All right. So,
well, should I start the introductions?
so I'll introduce you. I'll introduce.
Okay.
This is our fourth, I think, yeah. Fourth, yeah. Seminar in the seminar series here this spring. And today, our introducer or co-host is our administrative assistant in the Department of Chemistry and Biochemistry here at Andrews University. Her name is Miss Dana Johnson, and she happened to have been my TA. Isn't that right? She had to deal with me. Oh my goodness, I'm so sorry. I am so sorry. So that was a few moons ago. She does have a master's, correct, in physical chemistry, and has expressed interest in this fascinating topic of quantum time crystals. So, Ms. Johnson, the time is yours to introduce our speaker.
All right. Well, welcome to everyone. Today we have Dr. Sam Autti coming to us from Lancaster University in the UK, where he is a lecturer and an Engineering and Physical Sciences Research Council Fellow. He completed his Ph.D. working on superfluid helium-3 in the low temperature lab in Finland. And he has received several awards, the 2020 Young Scientist Prize for a range of superfluid discoveries. His work deals with interfaces between classical and quantum physics. And he's going to talk to us today about a new phase of matter called time crystals. I'm super excited to find out what is a time crystal.
There you go.
Okay, thank you very much for this very nice introduction. I'll do my best to explain what time crystals are. But to start with, I think I will be first explaining what helium-3 is, how we handle it in experiments, why we study helium-3, well, not only because of time crystals, but for many other reasons, and then only going to what time crystals are and how they emerge here. Now, as was said, I'm currently working in Lancaster, which is close to Manchester in the UK, so close to the northern border of England. But most of the experimental work, which I will describe, was actually done in Helsinki while I was there some 5 years ago. And well, some refinement and much numerical and theoretical work has happened since, as has much of the publication work. Well, this talk is about time crystals, as the title says. So I selected, out of my collection of propaganda images, I selected this thing on the left. And so this is a computer-rendered picture with about 2 time crystals. And it is surprisingly actually not particularly far from what they really look like. So you see here is a glass cylinder, which is partially filled with a transparent liquid. Helium-3 superfluid is transparent, and it is placed in our experiments in a tube like this. The real diameter is maybe 6 millimeters. I'll show you a photo in a few minutes. And then the time crystals, they emerge as these like magnetically spinning collections of little magnetic particles or quasi-particles, if you want to be precise. And they emit photons, which we can detect with suitable equipment. Now, the biggest deviation from reality is that the colors are really fake. So visible light is about 1 million times higher frequency than the actual frequency, which would be around 1 megahertz or so for each of these time crystals. Now, the liquid is helium-3. So first I need to explain what helium-3 is. Helium has two stable isotopes, helium-4, which is the regular stuff put in balloons, and helium-3, which is a rare isotope that in large quantities, such that would be, for example, able to fill a large container in our experiments. Well, in such quantities, helium-3 can only be collected from degrading hydrogen bonds on this planet. And that means that there are basically two sources, so the US and Russia. That's where it comes from, and it's a fairly expensive gas. And we have a very old stock in Lancaster, so that doesn't really concern us. And so while helium-4 turns into a macroscopic quantum system where all the atoms are doing more or less the same thing relatively easily, because it's a boson, and bosons like to do similar things with one another. Helium-3 is a fermion, so it contains 3 nucleids, and so therefore an odd number will give you a fermion. And that means that, well, fermions don't want to be doing the same thing as the neighboring fermions, and therefore forming a macroscopic quantum state is somewhat complicated. And in order to do so, we're going to employ a trick which may be familiar to you from superconductors, where a similar state is formed between electrons. So basically, we take 2 fermions and pair them up, and then the pairs can form a quantum condensate or a macroscopic quantum system. However, helium atoms, they, well, as we know, they have a finite core size. If you try to push them too close to one another, then there's going to be a hardcore repulsion. And so it will be energetically very costly to do so. While superfluidity is a low energy thing, so this means a pairing state, a wave function to describe what the 2 atoms are doing, which will put some finite likelihoods to these atoms being rather close to one another, is ruled out. And well, I mean, to use some jargon, this means that the S-wave state cannot take place. And so therefore we need some other one, well, for then much more complicated theoretical reasons imply that what we get is so-called p-wave pairing. But for the purposes of this talk, that only means that the spin and the orbital momenta of the pair are non-zero, and so will on average point in some direction within the superfluid. And this means that the wave function which describes our superfluid, which is often called an order parameter, not only contains or consists of a phase and an amplitude, but also the unit vector fields S and L. And what this means is that in practice, then the order parameter is a fairly complicated object. It will become a 3x3 matrix of complex numbers. And that has basically gives rise to a whole lot of phenomenology, among which a range of different phases, well, 3 of which are stable in the bulk. Further ones can be stabilized by putting this in some sort of confinement, like a slab or whatever. And then on top of the equilibrium, one can have a whole host of different collective excitations. So these are basically quasi-particles which travel in the superfluid but cannot go outside of it. And one of the quasi-particle modes is a magnon. Well, a few of them are magnons, but we are only concentrating on one of them today. And this is basically a quantum of spin waves inside the superfluid. And it is these magnons then which form the time crystal. Now, if we want to study the system experimentally, there is one major obstacle which we must overcome. And that is the temperature required. Unlike for helium-4, which goes superfluid at something like 2 Kelvin, or so 2 centigrade above absolute zero, this system only does so at 1 millikelvin, so a thousandth of a degree above absolute zero, which is a relatively low temperature. And then the interesting physics for time crystals, for example, is yet 10 times slower, so about 100 microkelvin, 100 millionths of a degree above absolute zero. And to get there in a macroscopic sample, so in like half a liter of helium-3 liquid, for example, is a significant challenge. And we might be using a piece of apparatus that looks, well, this is a computer image. I'll show you a photo in a minute. But basically, the helium-3 volume, the glass cylinder, is seen over here. That's where the time crystal will live. And then all of the rest of this, and much more to come, is just in place just so to provide the low temperatures that we need for operating the system. And here is an actual photo of what this will look like. So this is the cryostat we used in reality, and so to give you a rough idea of how this works, there is first the volume of liquid helium-4, that's about 4 Kelvin, and the whole thing is placed within that liquid, inside of which then we will put a steel can around these structures in the middle to provide a vacuum where different stages of temperature can follow one another without touching each other thermally. And so basically what we do then is, well, first we have some evaporation stage of helium-4, basically a chamber which is slowly filled from the bath outside. And then there's a powerful vacuum pump keeping the pressure low. And so this way temperature drops to about 1 Kelvin. And then we make use of a funny finding from, well, decades ago, that if you mix helium-3 and helium-4 in what is known as the mixing chamber, regardless of the start temperature, as provided that it's, well, low enough to start with, the temperature will be decreased further. To then force continuous mixing in this volume, we will be circulating helium-3 through there by first distilling it out in the distillation chamber, and then feeding it back in through these spiral-like heat exchanges in the middle. And this way we can get to a few millikelvin in continuous operation. But that's nowhere near enough. And the next step we're going to need options are rather limited, is magnetic cooling. We take a large chunk of copper, which here is covered by some shield, the brass thing at the bottom, and place that in a high magnetic field, let's say 8 Tesla. And we'll cool that to the temperature of the mixing chamber, and then remove the connection between them, and ramp the magnetic field down. And so the copper cools down as proportional to the change in the magnetic field. And all of this happens in practice in a machine, which you can see on the left. Now, well, this particular thing actually rotates while it remains very cold, but that's completely irrelevant for the experiments I'm describing. It's just a kind of a curious detail which I wanted to mention. The superfluid sample itself will be placed in this middle piece here. So on the left, you see this without the shield, the gray shield. So here you finally see this glass cylinder. It's about 15 centimeters long and 6 millimeters in diameter, where the superfluid sample is going to be contained. Inside the cylinder, there's nothing there. We'll place some coils outside of it, but inside it's just a smooth glass wall. Now, as a curious detail for many people who are following what's going on in contemporary physics, I'll mention that if you follow quantum computing news, especially those regarding the most popular type of construction, which is superconducting qubits, But then with all likelihood, that work is being done at IBM or Google or you name it in a blue force refrigerator, which operates well, in many ways in a similar fashion as the machine which I've just described. And this company, well, it was founded by Rob Blauvgers, who is the guy on the left, and he did his PhD in the same group where I did mine. I left more or less when I was starting. He left to start this company back then. So that's how you currently build a prototype quantum computer, if you wish, or where at least what kind of equipment you use for the cool down. Right, now that's how we cool helium-3 to the operational temperature. But why do we want to do it? Well, to explain that, I've stolen a slide from a theorist in Helsinki called Grigori Polovic. Now, in the middle here, you can see helium-3, well, which means the superfluid, and around it then, with various sorts of theoretical and conceptual links, is basically all other physics that you've ever heard about. He likes to call this the universe in a helium droplet. But rather than going through all of these details, I will just pick a couple of examples. And perhaps the most famous one is related to the Higgs boson, which was discovered in CERN about 10 years ago. Now, that's intimately related to the Higgs mechanism. And these are things you probably have heard about before. What you may not know is that the Higgs mechanism was originally called Anderson mechanism. And it was a piece of superfluid or superconductor theory, if you wish, where it then was borrowed from by Peter Higgs and Fellows, and it became a part of the contemporary standard model. To give you an example of something which moved in the opposite direction, there was a speculative cosmological idea that some topological defects might emerge in the early universe in some phase transitions that require expanding the standard model in certain ways. And while this idea, known as the Kibble mechanism, may have fallen out of fashion in cosmology, it was taken by Zurek. It's now known as Kibble-Zurek mechanism, and it creates topological defects, for example, quantized vortices in condensed matter systems. And in helium, this was discovered in 1995, maybe 6, don't remember, something like that. And since then, it has been seen in various other systems as well. Well, I might continue by saying that, the concept of quasi-particles in general was also a piece of superfluid theory a long time ago. Or I might tease you with the fact that the helium-3 can be used as a dark matter detector, potentially. And we're actually working on this idea of building a detector. But that's not the topic of this presentation, and I'm going to skip that. And instead, I'm now approaching the point where we can start talking about time crystals within helium-3. And for that purpose, we're going to place a few coils around our glass tube. So this is a computer-rendered image again, a bit different style. And so here you see the superfluid is in the middle, and we placed these brown coils in a transverse orientation around it. And so this way they allow, by putting in a radio frequency signal, we can create these magnetic quasi-particles. And then by just sitting around and recording the voltage, which is induced by the spinning magnetic motion that the quasi-particles are associated with, we can record a signal and observe what the time crystals are doing, or Now, we are now calling this a time crystal, but actually originally when we started this work, and for most of the papers I've listed here where we've discussed these physical observations, we're calling this a magnon BEC, so that's a Bose-Einstein condensate. These two concepts aren't identical, but the BEC, which is associated with some synchronous motion, will also be a time crystal. If I show you an example of a processed signal from an actual experiment, what's going on here is we are continuously pumping the system at some frequency over here. So frequency is on the x-axis and time is on the y-axis, and then the color gives you the intensity of the, or Fourier decomposition of the signal which was recorded from the coil, if you wish. So we're pumping at some frequency, but the magnons go to this what is the ground level in the confining trap, and then they form a condensate there, which lives for a relatively long time, several seconds after we turn off the pumping here. And to those of you who know what a time crystal is, I mean, this is basically it. But before I explain why, I probably need to explain what a time crystal is. Now, many people, at least those who have read anything about time crystals, might say that they were invented by Frank Wilczek, the Nobel laureate, and published in a PRL about 10 years ago, 2012. But you would be wrong in a sense that this was certainly not the first time time crystals in a similar meaning appeared in a something that was recorded. And what I mean by that is the first time this actually took place, as far as I know, was in the BBC TV series Doctor Who in 1976. And I actually have this episode on my laptop here, so if you don't believe me, I can show you. And I mean, the definition they use is not particularly far from the present one. Not going to show the video now, but well then, yeah, Frank Wilczek came 4 decades later, so it actually took him quite a lot of time to pick up and refine the idea, surely, in his paper. And so 10 years later, well, we have a bit better understanding of what time crystals are and what they are not than even this original scientific publication. And the most important thing is that a time crystal is a phase of matter where in the ground state, the system is in some synchronous repeating motion in the absence of external encouragement. And if that sounds like a perpetual motion machine, that's because it is a perpetual motion machine. And therefore, time crystals don't really exist. But in physics, if you think about it, most concepts that you will find in a textbook, for example, don't really exist. So the idea that you'll use some useful approach to describe phenomena which aren't precisely like this approach would imply isn't actually that dramatic. And that's more or less what's going on here. And if we inspect it a bit closer in quantum physics, there are many funny things. And one of them is that if we keep our eyes closed, it's actually okay if something keeps moving forever, which is to say, if it's not being observed, or even if it cannot be observed, then motion forever is just fine. And so then we might guess that we need to find a way of somehow weakly or only occasionally observing our time crystal motion, and then it will be fine, or in principle at least can be created in the lab. And then there are some other requirements, like, okay, we may need to create this system somehow in the beginning, but if we do so, the period, for example, of this motion should be independent of the way that we use for creating it. So, for example, the drive must not set this period, but it must be somehow spontaneously forming. Okay, so this is basically a dynamic phase of matter, which keeps moving the same way and always returning to where it started from, and so on. If we jump back to our signal, which you already saw, this is not particularly far from what I've described. So we are driving at some frequency here, but the system turns out to use some other frequency and keep moving at that frequency for a not very short time, considering that the motion that happens at 1 megahertz. So 20 seconds is like, 10 to the 7 periods or something like that. And if we look at even closer to the point where we've got the pumping on, what we actually see is that by adjusting the frequencies, it may happen that we have 2 time crystals in the same volume. So these will just overlapping states in the trap, if you like. And if the frequencies are incommensurate, so not compatible, if you wish, then the outcome will be motion which is aperiodic, but kind of repeating like the sum of the 2 sine waves in the blue one here in the middle. And so if we follow this language of time crystals, using this, like, well, what we do mathematically is moving between space crystals and time crystals, guided by Fourier transform of both things, if you wish. So repetition in space and repetition in time. Then this thing will be a quasi-crystal. So that's the space analog of what's going on here. So it's just a structure in space which doesn't repeat itself but fills the whole space anyway, and it's made from some simple components. Right. Well, if we then take our 2 time crystals and pull them apart, so instead of placing them in the same volume, we place them in right next to one another, we'll get what you saw in the beginning. So we've got the 2 time crystals, the red one and the blue one, and they are just touching one another in the middle. Now, arranging this is not particularly easy, but I'm going to spare you the technical details of how it's done. I'm just going to say that we can do this, and these are 2 stable positions for the clouds of magnetic particles with their magnetization spinning around constantly. And so the idea here is that okay, so if our time crystals need protection to exist in the first place, I mean, they may decay very rapidly or not even exist in the first place if we are observing them very strongly, then it may not be so straightforward to create interactions between 2 separate time crystals. It's not obvious that this can be done in the first place. That's what we're trying to get done here. And it turns out that if we arrange this, well, nothing collapses, no problem. They live on as you would expect. Someone's okay. And so to show you the experimental signal which comes out from this particular system here, there are now 2 time crystals. The axes have been swapped. I'm sorry for that. So time is now on the x-axis, and the frequency, where we've subtracted some large frequencies on the y-axis. But otherwise, this is the same as before. And the 2 time crystals. So the blue one is this top trace here, and the red one is the bottom trace. And then what we see, as should be, based on simple quantum mechanics, where we're seeing that there is actually population exchange between the 2 systems, which is here seen as this sideband, and there's a weak sideband at the bottom also, at a particular frequency given by the distance of the 2 main traces, which is, well, basically the sideband is as far away from the top trace as the top trace is from the bottom trace. And this is a well-known phenomenon called Josephson effect, AC Josephson effect. between two macroscopic quantum things. We can do something more complicated. I'm not going to bother you with most of the detail in this picture, but what I will say is that that this notoriously complicated construction of layered quantum systems within one another, it can be then condensed into a simple mathematical description here. This is the Hamiltonian of the two time crystals. And as described by this thing, for example, if we do something like we make the two frequencies go across one another, then population will move from one state to the other state, and the frequencies behave in a certain way, and all of this comes as described by the Hamiltonian. So basic quantum mechanics as you apply to the system is beautifully working. We can well, there are other things we can get out of here. For example, so this these diagonal terms, this omega b, small omega b, and small omega s, are the frequencies of the two time crystals. And then the off-diagonal elements, these capital omegas here, they are the coupling, so basically the overlap between the states. And we can measure that, and it's shown in the two bottom panels. But I'll just say that this works also. And so perhaps historically speaking, one of the most interesting aspects of this story is that while we are now using the kind of minimalist theoretical description, which contains this essential physics, which is the time crystal language, this isn't the only way of talking about these things. And so, well, one way of putting that is that I don't know, the Nobel Prize for Bose-Einstein condensation was given out for work done in, well, was it 20 years ago or 25 years ago, something like that. But this BEC, which I was talking about, which is the same thing as the time crystal, was actually originally observed in the 80s, well before that work, and people just didn't understand that it was the BEC, and they were describing it using some kind of more rudimentary theoretical tools and a completely different perspective. And from that on, then, well, people derived a Schrödinger equation, which led to the BEC picture, and then moved on to what we're doing now later on, which also guided some of the experimental work in well, the useful directions. I think I've used 25, maybe 30 minutes now. So I think I've got a couple of minutes which I can use. Well, I can still use.
Yeah,
and
you could do 10 minutes or so more.
Yes. Okay. Yeah. Thank you very much.
So
I could keep talking about time crystals for a very long time, but I thought that this is kind of heavy enough in terms of detail already. And I'm going to show you another research avenue we pursue in Helium 3, just very briefly, because I think it's particularly exciting also. And that one is shown here. I mean, so mechanically, what we are doing, we've got some well, a superconducting wire resonator in the liquid, but this is essentially just a rod. So you put you stick a rod inside the liquid, and you move the rod. The kind of the most basic experiment with a liquid that you can imagine. And then we're trying to understand what happens in the liquid when you do this. Now, there will be some thermal excitations, so basically broken Cooper pairs, if temperature is not at 0, but these would vanish exponentially when we decrease the temperature, so they can be eventually neglected. and the bulk of the liquid turns into a vacuum. So literally, if you move the rod around, there's zero force exerted on it. And so one might think that the story ends there, but it turns out very, very close to the surface of the rod, there is a layer where the superfluid wave function is distorted. And in this layer, it becomes a lot easier to break the Cooper pairs than in the rest of the liquid. And so the consequence of that, with some experimental complications, is that if I move the rod, and if I don't, well, I mean, if I do it really fast, or if the rod is very hot, well, then the superfluid will be broken. But if I do it slowly enough, and slowly enough might be less than 10 millimeters per second, for example, at low pressures, then the bulk doesn't know anything about this. But I'm giving energy to this like 100 nanometer thick surface layer, where it then flows along the surface away from the point where it was imposed. So a bit more technically, what's going on is we've got some bound states in the surface layer, and they react to the flow of the superfluid around or along the surface, being shifted by the flow. And then they gain some energy. And we know all this because if we exceed then there's 10 millimeters a second, some of these states will escape to the bulk, where we can easily measure the release density. And so this gives us a snapshot of what was going on at that instant. And then working backwards along a complicated theoretical construction, which I will not explain, we can work out that we've got some diffusion actually going on in the surface with a time constant, which is like 10 milliseconds or so. And astonishingly, this means that in this system, if temperature is low enough, it's basically a two-dimensional liquid rather than a three-dimensional one. So if I stick my hand in there, move it around, the bulk is empty. There's nothing there, although there is a liquid, but it just cannot interact with your hand. And if I touch a source of heat, so some hot surface, then the heat will immediately start flowing along my finger. And if I stop touching, then the flow stops. Or if I move my hand, the surface will heat up, and then the heat is drained along the surface. Well, this is work in progress. But we believe that this is the right interpretation of what we are seeing in the experiments. And if that's true, it's essentially the first big quantum system where we can actually tell you how does it feel like to touch quantum physics. So I think that's very exciting. And now, well, I probably have a few minutes left, but regardless, I'm just going to conclude here and thank you for your attention.
All right, thank you very much. Dana, you want to say anything? I have questions. You have any comments or questions? Okay, so go ahead, Dana.
I'm just overwhelmed. I catch a little here, a little there. It inspires me to look further.
So well, my fundamental question is just like simple, direct, straightforward, which is, are time crystals real? Because at one point you said they are, and then they aren't. So I have a newspaper friend, okay, for the general public. If I were to write an article now, are they real?
It depends on what you're after.
Okay.
So it would be easy to argue that they're not real. But then again, almost all physics is like that. I mean, apart from some fundamental theory, which maybe is actually true, but most physics ideas we do are just so that we can, allow us to understand nature. they're not actually fundamentally correct, so they're approximations.
Oh,
And in that sense,
okay.
it's not a big deal. Then really the proper question to ask would be, so if we use this language,
Mm-hmm.
do we learn something? Like, does
Okay.
it predict something? For example, okay, so let's assume we do have time crystals, and that makes sense to talk about them with this language. Or does it mean that we can melt it? If we melt it, do we get a liquid, in a time liquid? What does that mean? Does it make sense? Does it not make sense? Well, we don't have an answer to that, but if you start building this way, and the answers are yes every time, then that's kind of a concrete answer. It will tell you that yes, it's useful. It teaches you something about the phenomena. If the answer is no, then probably it's a waste of time.
So okay, does time crystals only exist in superfluid conditions?
No, there's a range of systems where people have found behavior which is at least very close to the original definition. Well, admittedly, the most obvious examples are other quantum condensates, which are maybe not liquids like a superfluid, but say a gas, a quantum gas. This is what the atomic BECs, these Bose-Einstein condensates, would be originally. But it's not only that. You can do, I think one of the early papers was about some impurities in some diamond structures, I think, so nothing to do with quantum gases or fluids. The further you go from the physical system that I study, then the more laborious it becomes to actually understand what they're doing. So it would take me a while to remind myself about what they are doing.
Yeah, right. The other question, and then I think there's another question in the chat that I have is like, okay, so we know crystals can have different not states, but different particles. So there are organic crystals, there are ionic crystals, sodium chloride,
Mm-hmm.
there are metallic crystals.
Mm-hmm.
So how could we visualize a time crystal? Because we could,
Mm-hmm.
Like a sodium chloride, we know is this cubic structure, right? Alternating
Yes.
anions and cations and stuff. With metallic crystals, we have quote unquote a sea of electrons around,
Yes.
So how could we visualize?
Well, if we do kind of strictly theoretically correct descriptions, then well, the physical space is three-dimensional, and so you have these three-dimensional lattice structures that make the ordinary crystals we know. Well, the time domain is one-dimensional, so all these crystals are 1D, meaning that they are on an axis time, they repeat on that 1D axis. Now, well, you can imagine a 1D lattice, of course, in principle. I mean, or at least 2D lattice is easy to do. That's just like a layer of carbon atoms. These actually exist. Right. But yeah, 1D maybe not so much. You can get close with nanotubes. So this would be like a layer of carbon atoms which is wrapped around itself, and then it's almost 1D, but not quite. I mean, there's multiple atoms making the second dimensions rather than one, but it's only a handful. So it's not, I mean, conceptually it will be something like that if you really follow the mathematics.
Okay. So one of our students is asking, this is Ian, how did you decide to go into this research? Yeah, that's a good question.
Yeah.
Yeah.
Well, so if you listen to people who you think are somehow successful, they will often tell you all sorts of bogus explanations about how they were so great, but in reality there's lots of luck involved and lots of just like random outcomes. I mean, you need to work hard and all that, but on top of that, then I mean, control doesn't really always exist. And so in my case, well, I mean, when I was really, how I got into this field was in Aalto, in the university where I did my PhD. I did my undergrad studies also there, and in my second summer, I was looking for an intern place, which was a regular thing to do there. And so the research groups in the university would offer these places in a centralized system, and you applied to any number of them. I applied to a handful, and in the end, I was selecting between some fusion reactor simulations and some quantum devices, and then superfluid helium-3. And I ruled out fusion simulations for reasons I don't really remember, and quantum devices because I thought the guy running the group was a dick, which turned out to be true. And then it was helium, and I liked it a lot. Well, I mean, to be fair, the low temp lab in Helsinki or in Aalto was very famous, so that probably contributed to the decision to go there.
Oh, okay.
But maybe to give you a taste of what's the kind of randomness which often occurs is, you know, when I was I defended my PhD degree or thesis, and then I needed to find a postdoc place. It was obvious to me that I liked science enough to like take the chance. I mean, to try and pursue a scientific career, at least to see how a postdoc would be like.
Mm-hmm.
But I didn't really know where to do it or what to study. And actually, one thing we had been doing in Helsinki was Majorana fermions. So these are some weird quasi-particles. And quantum computing was a hot field already back then. It's 5 years ago. So I thought that I would go to the Microsoft quantum computing operation in Copenhagen, where they used or claimed to be using these Majorana states for making qubits. So these building blocks of a quantum computer were supposed to be all sorts of great advantages that you gain by doing that. But I applied and they interviewed me, and eventually they refused, and I was very annoyed. And so the joke is that a few years later it turned out that they had been fabricating data and publishing it. And so it was very lucky that I didn't get accepted. And I mean, certainly none of my own credit there. It was just like a twist which was needed.
Yeah.
And so now I'm here.
Yeah, that's really interesting. So you, in other words, you weren't really looking to do research with time crystals. It just sort of emerged from what? No,
I mean, and of course, to be honest, that we are now calling them time crystals is useful. But I mean, there is the propaganda aspect also. I mean, it makes publishing papers easier if you do that rather than calling them spin superfluidity or something that they used to do in the early times.
Okay. Okay. So I don't know if Liebert is still on. Did you have a question or comment?
Yes, I'm well, not that I'm well knowledgeable in this area, but just the concept, because I could understand, you know, if you had, let's say, for instance, if you put the helium together, you would think that maybe there's some type of crystalline structure, you know, as it condenses itself. And how did you know that it wasn't doing that? And it was packing as time thing.
Okay, so crystalline structure would be a solid. And helium actually does form a solid, but only at a very high pressure of 35 bar or so. And then this time crystal actually has nothing to do with the crystalline helium. It's just motion of magnetic particles inside there, which is very easy to observe if you put some coils around, because it will give you a sinusoidal signal which doesn't die very quickly. It just keeps going on its own. Well, how do we know that it is this thing? Well, lots of work went into, so if we jump back here, this list of papers and many other papers written by other people are actually about understanding what the system is and why it behaves the way it does. And then a whole lot more papers are just about understanding why helium is a liquid and how the liquid behaves at low temperatures and when it becomes a solid and why that happens and all these things. So of course there's lots of work which goes into just the basics of how you manipulate the system in the first place.
I'm just saying that, it was their theory, a basic theory about
So
data didn't fit that theory, or looking at the molecule you realize that to explain the behavior it couldn't be a type of normal crystalline structure and it had to be another type of thing, and you developed the time crystal. Which one?
Well, so I don't know originally whether, no, actually I do know. Originally, a long time ago, they just observed this signal in, well, what they knew was a superfluid, or at least thought, and they didn't understand it very well. And then it took a long time before some sort of systematic understanding emerged, guided by several experiments, and an even longer time to simplify the language enough so that it can be kind of condensed into some simple short concepts like a time crystal. But yeah, so I should emphasize that we could perfectly well, where is it? Be just talking about we could perfectly we could just talk about the BEC. That
Let's say
would work.
that you have a spectrum because you're monitoring it by nuclear magnetic, and then you get the spectrum, and then when you wanted to understand the spectrum that you got, you had to apply Fourier transformation to the thing, and then you realize that it's made up of the ground state of that. Okay.
Well, I mean, then of course after that came as soon as we understood how to create it, then there were lots of experiments where we just changed, like what happens if we change this, what happens if we change that, how about this, and then there was actually several years of doing all that.
So you said that it was a ground state and an excited state. Can there be a type of crystalline structure where you have more than just the ground and excited state, but many excited states?
Yes, in principle. Although if you make the particle density very high, then they tend to talk to one another so eagerly that the particles all go to some single place rather than all of the possible different ones.
Okay, all right.
What's the cost of helium-3?
If you really went and bought it now, I think this is between $5,000 and $10,000 per liter of gas.
Oh wow!
And then that's atmospheric pressure and temperature. And then to turn this into a liquid, it condenses by a factor of 700 or something like that. So an experiment like this will contain easily, I don't know, at least $500,000 of helium-3.
My gosh.
So the first rule of a graduate student in the lab is you don't lose 3.
Actually, when I went to university in England, actually, when they did the assessment of universities of physics department, they wanted to close down a lot of physics departments in Britain, but they ended up closing the chemistry because it was important, because the physics department produced the helium and physics was non-existent if you didn't keep the physics departments open. So although the physics department scored way lower than the chemistry departments were merged because of the advantage of physics department producing important condensed materials that could not be done by any other way. And later, the physics departments became the best departments in Britain. And so therefore it showed that, you know, short-termism could have changed because physics in Britain was weak in those days. And they kept it over, and then it became stronger, even stronger than the chemistry. So it just says about administrators and
yes. Well, I'm afraid politics hasn't become much more far-sighted in the present day. So.
Okay, well, let's see. Do we have a student that has another question? We will probably end with that. If there is at least one more question or comment. Yeah, this kind of forces me, I know, to go back and look at crystalline materials, and because it sounds pretty exotic.
It is pretty exotic. I mean, it's basically physicists coming up with fancy names for things to an extent.
Well, it's good that you've expanded our vision or concept of crystals. Can
I ask one basic question, Mark, and ask Desmond?
Okay.
Because when we talk about quantum materials, you know, in terms of in the other direction, this to me looks more favorable because you'll be able to get more different states from this to be able to do quantum whatever computing or whatever you want to define it as, than what the direction they may be going. So do you think that the quantum computing will be more in this direction than the other types of directions?
Well, a proper answer would be probably take an hour or so, but right. So in quantum computing, as you presently would hear about it, there is one central concept where basically the computation power comes from, and this is the ability to create entangled states between different particles or whatever entities in the construction. Now, entangled states allow various weird quantum mechanical, well, a handful of weird quantum mechanical operations, which then make these computation algorithms kind of, well, they follow different rules than those of classical computing. Here, there are no entangled states. The reason why large quantum systems don't contain relevant entangled states is not theoretically understood, but it is an experimental fact. So basically, if we derive a description of, well, the simplest thing would be an atomic BEC, or well, close to helium-4. So just a wave function with an amplitude and a phase, a complex number. That should be our final answer. The way this is derived is there is a step where we assume that entanglement disappears. And it works. It gives you all the right physics. So we know it's the right answer, but we don't really know why. I mean, you will encounter this mystery in various other shapes and forms in other corners of quantum physics, and it is so for that reason you can't do quantum computation with this system, and for that this is also, generally speaking, the reason why it's not clear that one can actually build a quantum computer in practice, because we don't know why in large systems entanglement tends to disappear.
Oh, okay. So the quantum computing could be a dream.
Well, so in theory, no problem. But in practice, classical physics has to appear at some scale.
Okay.
By some pretty reliable mechanism. And we don't know what that is.
Okay. Okay. All right. Thanks again for insights.
No problem. It's a pleasure.
And continued success.
Yeah, thank you.
yes, in masking or unmasking these mysteries, these quantum mysteries.
At least, thank you very much because until I saw your title, I didn't even know such a thing existed.
Same here.
And so therefore, I understand the process because I'm a physical chemist and I deal with spectroscopy. So I understand the basic signals coming together, but I don't know enough. But I'll know enough in a few months' time because
Okay. All right.
Thank you very much.
Again. Okay, have a good one. Take care.
Yeah, cheers.
Okay, bye-bye.
Thank you very much. Take care, Desmond.
All right, thanks.